Test. Hello. Test. Hello. Yo. Test. So I was at the gym because my friend um was in town randomly. He's just in town and we caught up. It's chill. And he asked me, it was me and some like two other high school friends, so the four of us, and they're like, "Yo, come to dinner with us." I said no, got to put in my 90 minutes of MCAT. I just turned them down. They're like, "Oh, it's okay, just hang out with us when you become a doctor." And they're like, "Oh, you'll be busy when you become a doctor. Hang out with us when you're like actually practicing." They're like, "Oh, he'll be busy when he's practicing too." And they're like, "Oh, hang out with us when you're retired." So yeah. This site is so bad, bro. Holy muffin. This website is so slow. Please. When are they gonna update this? When are they gonna fix the servers?
In this video, we'll be discussing substitution reactions, and we'll focus on the SN2 mechanism. Now, before we get into the details of the reaction mechanism, we need to be able to recognize what a substitution reaction is to begin with. So what we're going to be looking for is how the bonds change over the course of a reaction. So in a substitution, we're going to see that we exchange one atom or a substituent for another. So in this case, some sort of leaving group will be attached to one of the starting materials and will get displaced by an incoming nucleophile. Now, the bonds that change are the bonds to those leaving groups and nucleophiles, and they both happen to be sigma bonds. So we're looking for the breaking of one sigma bond and the forming of a new one to signify a substitution reaction. Now there are three players, as you can see in this reaction. We've got a nucleophile, the thing that the nucleophile attacks, or the electrophile, leaving group, which is attached to the electrophilic molecule. So let's do a quick review of those three species. The first is the nucleophile. And what makes a good nucleophile is that it's got some sort of negative charge or else a lone pair of electrons. So the more negative the nucleophile is, the better it's going to be able to donate those electrons to make that new bond. In terms of what makes a good electrophile, we're looking for some sort of partial or full-blown positive charge on one of the atoms of the other component of the reaction. That's generally that atom attached to the leaving group. So the greater this partial positive charge is, the better the reaction is going to go. And then finally, the leaving group has to come off. And so if I have a good leaving group, it's going to come off more easily. And this leaving group will depart from the electrophile if it's going to be more stable in solution. So what we're looking for is a weak base in order to be able to take the electrons of those bonds and come off into solution with them. Now let's look at some details of the SN2 mechanism. So we're starting off with a substrate that, if you take a look at my electrophile here, here's my electronegative iodide. And iodide happens to be a pretty good leaving group because it is a really weak base. Now my cyanide ion, my Cn-, is actually a great nucleophile. And so the combination of these two things means that this reaction happens pretty easily. What we're going to find is the nucleophile comes in and does its electron donation at the same time that the leaving group is leaving. So this is what we refer to as a concerted reaction, meaning it all happens in one step. And in order for both of those things to crowd around that central carbon at the same time, they have to approach from opposite sides of the molecule. So we refer to this as a backside attack of the nucleophile. And what we're going to see is that as the nucleophile comes in, it starts to take these three atoms that are bonded to this central carbon and kind of flatten them out. So we'll see that as the new bonds start to form and the old bonds start to break. As we go sort of this way to our highest energy species along our reaction path, we get this thing called a pentavalent transition state. So penta, meaning 5. It looks like there are 5 bonds around this carbon in the middle, but the dotted lines to this, the nucleophile and to the living group, are just partial bonds. So these are showing a new bond is forming, and an old bond is breaking. So we usually show transition states in these square brackets with this double dagger on the outside. And as this band continues to form and this one continues to break, we will end up with our final product, where we can see the leaving group has left and the nucleophile has attached. Now this transition state is not something I can isolate in solution. It's not an intermediate, it's a high energy species, and I can't put it in a bottle, I can't put it in a flask. So the other thing you should recognize here, as this bond continues to form, that these three groups that were sort of in the plane perpendicular to your computer screen end up being sort of pushed to the right-hand side of the molecule. So what's happened is the three groups that used to be pointed toward the left of the molecule end up on the right-hand side of the molecule. So we see that this reaction goes with inversion of configuration. To whatever the stereocenter happens to be, ends up being inverted over the course of an SN2 reaction, because the nucleophile and the leaving group are changing bonds at the same time. So in this particular example, we start off with an S stereocenter, and we end up with an R stereocenter as a result of the inversion. Now the other things that I want to sort of stress here, in terms of the SN2 reaction, we've already talked about the idea that the mechanism is a one-step process and goes through this transition state, and we see that the reaction goes with this inversion of configuration. Now the other things we want to consider are, it will slow the reaction down as this hydrogen and deuterium atoms were actually larger carbon groups, because that makes the attack of the nucleophile into this electrophilic carbon slower. So the structure of the substrate helps to determine whether the mechanism will go through this one-step process, or whether SN1 is the better route to go. So the more substituted this carbon is, the less likely SN2 is going to be the mode of choice. So if that substrate gets so substituted and so crowded, we won't actually see a tertiary substrate go through an SN2 process. Now when we think about the kinetics of this reaction, and write the rate law, remember that the rate is dependent on the concentrations of whichever molecules bump into each other in the slowest step of the mechanism, or the rate determining step. But since there is only one step to this mechanism, and both the nucleophile and the electrophile have to bump into each other in order for this new bond rate law, and that means that the type of nucleophile that I use has a big impact on the SN2 mechanism. Product solvents also favor SN2 over SN1. In this video, we'll be discussing what it means for a molecule to be chiral. Now, if an object, whether it's a molecule or something macroscopic like your hands, is to be considered chiral, what that means is that the item is not superimposed, and vice versa. But if you a molecule looking back at it from the mirror, line up. But the methyl in the back would line up with the hydrogen and vice versa. This methyl in the front would line up but this hydrogen. So they're not completely superimposable. So So what that means is that this is a chiral molecule, and its mirror image is a different chiral molecule. These two images are not the same structure. Now, the easiest way to identify at a quick glance whether something is or is not chiral is to identify whether it contains a chiral center. And it's almost always going to be the case that some substance that has a chiral center will be a chiral molecule itself. Now, there are a few synonyms for chiral center that you might come across on the MCAT, so take a look at those here. But what will be true about a chiral center is that it will be sp3 hybridized. And because of that, it will have a tetrahedral geometry. And that means that it has 4 substituents attached to a particular carbon. And when those things are different substituents, then the substance will be chiral, or that particular carbon center will be a chiral center. So you need to be able to look at a molecule and identify, are there any, and how many are there in any given molecule. So if you look at the molecule on the left, one of the things that often tends to be a trap for students is that when you see a wedge or a dash. This sort of perspective in a molecule, oftentimes we assume that that's going to be a chiral center. But in this case, that happens to not be true. While each of these carbons with the OHs on them have hydrogen in the back. Because of the symmetry of the ring, there are no chiral centers here, so if I examine them on the top, the OH and the hydrogen are different groups from each other. And when I go around this side of the ring, I get a CH2 group. And I get a CH2 group on this side of the ring, so they're not different yet. And if I go to the next carbon in the ring, these two carbons are at the opposite, and therefore the centers. Now for this structure in the middle, drawn in a Newman projection, we see that that's not the case, so the carbon in the middle has 3 different substituents attached around the outside. Hydrogen, methyl, circle represents the carbon in the back this carbon is attached to. So the fourth group is this carbon group that's different from the methyl group in the front, because this carbon group has a chlorine on it, for example. So that circle of carbon is chiral. And in addition, this circle that represents a carbon is also chiral, because it has 4 different substituents as well. The chlorine, the hydrogen, the methyl group, and has 2 chiral centers. And the one on the far right, if you take a look, things we can eliminate quickly are things like the CH2 groups, because they don't have 4 different things, they have 2 hydrogens, so all the CH2 groups are going to be achiral centers. The sp2 hybridized carbon in the carbonyl group cannot be chiral. Your methyl groups can't be chiral. Those are CH3 groups, and we're looking for 4 different substituents on the chiral center. The carbon that contains the 2 methyl groups is also not chiral. For the same reason, the CH2 group would not be chiral. So now we're down to 3 final carbons, and if we take a look at these guys, these are all chiral centers. We have 4 different substituents attached. For the nitrogen compound, or the nitrogen center, we've got the H2 group.
That's a W. Okay, bro, you don't need to freak out. Work, bro, please. Please work. I'm not done with you. Should I restart my computer and then come back?